Okay, so let's think of where we are at this point in terms of the equations that we've been building. In other words, Maxwell's equations. So we have Gauss's law for electric fields. Right? So the integral of the electric field over a closed surface, dA being the surface element, is equal to the charge enclosed divided by epsilon naught, some number. That's the integral version of that. And we know that there is a differential version, which we have not explored mathematically, the concept of the divergence of the electric field being equal to the charge density over epsilon naught. Right, so these two equations are equivalent to each other, and we've used this version to do all of our calculations. For magnetic fields, we know that Gauss's law for magnetic fields, that the integral of the magnetic field over a closed surface is always equal to 0. That's equivalent to a differential version, which is that the divergence of the magnetic field is always 0. Magnetic fields don't diverge from current, they circle around current. And so, in fact, there is a non-trivial, if you will, loop integral for the magnetic field. So we integrate the magnetic field around the closed loop, B dot dl. dl represents a little infinitesimal element of the loop. This is equal to some constant mu naught times current enclosed through the area that has this loop as a boundary. And there's a differential version of this, which is basically, in words, saying that magnetic fields curl around current. So the curl of the magnetic field is equal to mu naught, the same constant, but times the current density. And then there is a version of the curl for the electric field. So the closed loop integral of the electric field is equal to minus d phi dt, where phi, or phi b, is the magnetic flux. And the differential version of this, of course, has curl of the electric field having something to do with the changing magnetic field, time-changing magnetic field. Notice that these equations are not symmetric, but we've argued that they are becoming more and more symmetric in the sense that if we might replace magnetic field with electric field and find that the equations seem to have the same form. That's possible if, for example, when we look at this one, there's also a time-changing electric field term in this equation, which would then change this equation. Then we could argue that this would have to be non-zero in general, and this one as well, for it to be compatible, for it to be symmetric with this. It is true that there is an extra term here and here, by analogy with this one. And we can see this by the fact that when we integrate around a closed loop and then consider the current going through that closed loop, for example, we have the infinitely long line of current, with current I going through there. We integrated, if we integrate around a path that, if this is the current, where the current goes through here, and we consider I enclosed here, right? That's the I through an area that has this as boundary, which in this case is this. But what is that area? Is it just in this case it looks like a circle, but it could be any area. It could be, where we consider some kind of tube-like structure, and we notice that in this case, there's always the same amount of current going through this part over here, or maybe it could be a cylinder or something like that. So there's still, if we consider the area, so that it has the same boundary, this is the boundary, and this is the area, we still, for the infinitely long line, we still have the same current going through it. So it doesn't matter whether we consider this to be the area or this part. But if we are in a circuit where we have a capacitor here, and we're charging the capacitor with current, then things become a little ambiguous. Because if I consider the area that goes through here, then it looks like there's no current going through there. And so, in fact, there's an issue here. We should be able to evaluate this for any area that has this as the boundary. And it turns out that we have to generalize this equation. And this equation, this one has a term that has the changing electric field in it, but that means that there is current in this situation as well. There's current in this region. It's just not conducting current. It's some other kind of current that has to do with the fact that the plates are charging up. And so we generalize Ampere's law to B dot dl equals mu naught times two terms that involve current. The one that we normally call I enclosed is really I conduction. And then there's current. So there's no I conduction through here, but there is an I displacement current called displacement current enclosed or enclosed. Okay, where in fact ID looks like this. And it has to do with the time-changing electric flux in analogy with this equation. So, in fact, the equations are becoming more symmetric.